hope my screen is visible.
Yes, it is visible. Yeah.
Yeah. Okay. First of all, good evening to all of you, and thank you, Dr. Ramakrishna and Dr. Raghu, for giving me this opportunity for this in this AICT sponsored faculty development program. So, as you know, this IoT or Internet of where everything is going towards smart. Everything is becoming smart. We are talking about smart devices. We are talking about smart things. At the same time, the research or the industry people are also talking about smart manufacturing, where how we can automate this entire manufacturing process and make it smart. So in that particular context, right, so I would like to highlight the need of IoT, which is Internet of Things, and its application in additive manufacturing process. The reason why I have chose additive manufacturing to be specific is very simple. That additive manufacturing process, as most of you would be aware, that is another booming area in the domain of manufacturing, where it has been well proven that additive manufacturing process has become quite a versatile process and actually help the people in a lot of sense in terms of making customized product and all those things. So if this two burst area, if you are able to integrate both of them, take the benefits of both of them, it would basically improve the productivity of the industry. Also, it would improve the process dynamics. So with just that particular background, and I think the pointer is also visible. Can just somebody confirm?
Yes, it's visible, Dr. Rahul.
Yeah. Okay. Thank you. Right. So with this, these are the three main broad contents which I would like to discuss in this session. First, sorry, we'll briefly talk about various types of additive manufacturing process with a prime focus on one of the category of additive manufacturing process, which is wire arc additive manufacturing process. Right. There are some specific reasons why I want to emphasize on this wire arc additive manufacturing process, because of its certain inherent advantages, which we'll discuss as we move forward. At the same time, we'll also talk about application of IoT, right? Why IoT is required, why it would be beneficial, as well as because IoT would be done with the help of certain sensors, right? So, which kind of sensor can help in attaining what kind of thing? So those kind of thing we'll see. And when we're discussing different types of sensor, we'll try to take certain example from additive manufacturing process as a case study and try to see how this sensors or the application of IoT, right, has helped the additive manufacturing process or manufacturing process as such to improve the performance. One thing I would like to emphasize over here, though IoT has become a thing for today's, maybe 5 or 10 years, but for mechanical engineers, using sensors to evaluate the quality of the process or quantify the process is being used by researchers for a very long time. But with the advancement of computer, with the advancement of big data and cloud computing, what has happened is the sensor data, whatever you are getting, what people used to process in offline mode, now because of this cloud computing and big data analytics and large computing facility, this has given the researcher or industry an opportunity to process this data in real time. And when you process the data in real time, the major advantage which we get is this. So if there is any flaw into the process parameter can be tweaked immediately so that we get the optimum condition, or so that we get the required mechanical and metallurgical strength. Previously, what used to happen is, whenever people were capturing the data, they used to process the data in offline mode. So even though they are able to process the data in offline mode, eventually the experiment has been done. So a lot of experimental efforts were required in order to get to the optimum process parameter. but with the application of IoT and eventually the use of IoT to make digital twin, which will emphasis in about this in a bit, right? It has given lot of advantages to researcher as well as industry to create a framework, right, which can tell the operator ki which particular condition would be an optimum one. So with that particular background, let's get started. So let's first start with a very simple example of IoT, how IoT could be helpful. I have taken this schematic diagram from one of the renowned publication. So, sorry. When we talk about IoT, the very simple definition of IoT has been listed over here, which says ki IoT basically means connecting the power of internet with different devices. So this IoT, like for example, nowadays we have smart fans, we have this Alexa, or Google has this iPhone has this Siri and all those things. So these are example of smart devices where remotely also with the help of internet we can connect to the devices and we can control them, right? So with that particular thing, it has given lot of flexibility to the user from the customer point of view, from the user experience point of view. This has enhanced a lot of sense, right? And in IoT, what happens? Different sensors share data with each other. It is stored in a cloud server and the processing happens. So if we want to extend this particular concept of smart devices into manufacturing, so what you can see over here, right here, this shows a schematic location of additive manufacturing. So let's say we are doing this additive manufacturing process, right? And in additive manufacturing process, we already had this CAD model, right? Now what we can do, we can create a digital twin. What is digital twin? Digital twin is basically the exact replica of the actual manufacturing process, right? So that is why the word twin. So what it goes as an input in the digital twin? So one obviously is the CAD file of the model. Second is output from the simulation. So we are aware about this finite element simulation. Now using this finite element simulation, mostly in context of additive manufacturing process, what we can get various information. We can get about the temperature profile, we can get about the temperature contour, how the temperature is distributed, we can get about the information about the residual stress, we can get about the information of thermal distortion, which is happening because of the change in temperature and associated coefficient of thermal expansion, right? All this information, right, can be fed into this digital twin. And how this digital twin is made? This digital twin is made using some kind of a machine learning and AI algorithm. So you basically train your model the way it is done in machine learning or artificial intelligence. You basically train this model. How do we train this model? We train this model when you're doing the experiment. We do lot of experiment which generates data, right? So what we do over here, here for generating data, we use various type of sensor. We can use infrared sensors, we can use acoustic sensor, which we'll talk in a minute, right? We can use spectral sensors, we can use other type of sensor. These sensors will generate lot of data for the manufacturing process. Now this data needs to be processed in order to understand what kind of feature of this data is telling us whether the process is good or the process is bad, right? And with all this digital twin, certain kind of analysis can be done which will tell us a limited set of data, which will give okay, within this data we'll get this kind of an output. For example, if you are working with 20 ampere current, 20 volt voltage and a velocity of let's say 20 mm per minute, in case of additive manufacturing process, we may get a mechanical UTS of maybe 200 megapascal or 250 megapascal, right? So with this particular thing, so this getting the strength of 200 megapascal or 250 megapascal, we generally used to get only after doing the testing with the help of UTM, right? So this predictions are possible with this. Now with whatever prediction data we will get, right, that can be fed in over here, right, which can also be used for quality check or inspection, right? So this is how you will get the quality inspection checked and all those things. And if there's a possibility, now this is a slightly advanced version, so I'm not going into that particular thing, but just I'm touching that particular thing. Now within IoT, people are also talking about AR VR, augmented reality, right? What augmented reality can help is basically it can help you to simulate this entire additive manufacturing process in order to understand how this process will look like. That means if we have one layer onto other onto the third one, right, whether there would be any kind of distortion or not, right, how this layer will diffuse within each other, all these things can be seen in a virtual environment with the help of digital twin. But again, this is not will not discuss much in detail about this augmented reality. We'll focus more about this particular part, how in situ monitoring, what kind of sensors can be used, right? And with the help of sensors, how data can be processed, right? So that some kind of machine learning process would be used in order to get certain information. This same thing can also be beneficial in supply chain, because in India being a very vast country, right, supply chain management or transporting the goods from one location to another and taking care of the transportation itself is a very big problem, right? So that is another domain with this entire data thing can be processed, right, and can be optimized, right? So in this today's session, we'll mostly focus on this additive manufacturing process. We'll talk about what is this additive manufacturing process and which kind of sensors can be used for real-time monitoring, right? Once you are able to generate the data and process the data, then making this digital twin is a second step, right? So we'll only talk about the first step in today's class, in this today's session, right? So let us first start with this additive manufacturing process, and let's first try to understand what is so significant about this additive manufacturing process, because of which everybody is talking about this additive manufacturing process in a large sense, right? Even there are a group of people who says maybe 10 years or 15 years down the line, right, this additive manufacturing process will basically replace majority of the manufacturing process, right? So let us try to understand this thing. So let me pose certain questions which are relevant to additive manufacturing process. First, what if anybody can manufacture anything anywhere? What do I mean? Right now, if you want to manufacture certain product, right, we need to set up a very big industry. You need to purchase a sophisticated equipment. There has to be an assembly line, right, which requires a lot of capital investment, right, and which because of which everybody cannot afford to initiate a business specifically if you want to manufacture a sophisticated product. But what if somebody is able to manufacture things wherever he wishes to, need not require a large piece of land, sophisticated machine and all. So if this kind of a thing will happen, this will make the life of industry as well as customer very easy. Second is, what if, so currently what happens, we require very large assembly lines, we require the sophisticated dedicated power connections, sophisticated machines and all. But what if we just need electricity, raw material and a computer to set up advanced manufacturing process, right? If we are able to do this particular thing with this simple requirement, that will reduce the capital cost tremendously. What if an entrepreneur, right, or a startup person want to start selling their product without purchasing tool and machine, and today there is an order, tomorrow he can ship the product. For example, in manufacturing, it's a well-known fact that if you want to manufacture, let's say, a product through casting, there's a lot of pre-production work which is required. For example, you need to make pattern, we need to make mold, we need to do the riser design, we need to do the gating system thing, right? We need to select which casting process we will use, right? How to make mold of it. So there is a lot of work which requires. So making any product at least have a lead time of 6 months or 1 year or 1.5 years, right? Which eventually adds to the cost of the product. But what if there is a process or there is a methodology in place because of which, right, if there is a demand today, I can immediately manufacture the product tomorrow and ship it that very day. With this particular thing, the customer satisfaction of the business will flourish like anything, right? Similarly, what if this kind of a customized product or this kind of a geometry, this is not that easy to manufacture with the conventional way, right? It will require a lot of machining, it will require sophisticated equipment. So that's why this overall product will become expensive. What if we want to reduce the overall cost? Right now, this we are mostly talking in terms of metals or smartphones. What happens if somebody has some problem? For example, in India there are a lot of burning cases. I mean, people get burned through fire because of accident or because of any other reason, right? They are disabled, right? Or heart had stopped functioning or anything, right? There is a bone transplantation which is required or anything. So what, and this are actually very complicated material from the material point of view. So the bioprinting, what I'm talking about here, what if we can simply scan the ear? See, scan the ear meaning, because each human being, the shape and the feature of the ear is different. So we cannot make one particular product which can fit for all human being. For each of the human being, it has to be customized. And whenever we talk about customization, the cost of the product increases. But what if we can simply scan the ear for whichever person we want, and we can print the ear using bioprinting, bio 3D printing, where you are printing using the material which is biocompatible. We fit the hearing aid and whatever electronics which is required and just ship it, or maybe put it into the person. So what will happen? The long medical process or the long waiting period which is required for the customization and all those things, that will reduce tremendously. And all this is actually possible, and it is actually happening with the help of 3D printing process, or what we call it as additive manufacturing process, right? So with the involvement of this additive manufacturing process, lot of advancement has happened, right? Which actually has helped human being or industry to evolve, to get a better product, right? What is this additive manufacturing? So I'll take some time to create a base for additive manufacturing, so that what will happen when in the second hour we'll start talking about this IoT and all, I need not again explain this additive manufacturing process and how it is helping in reducing the defects and all those things, right? So I'll try to make a base in the first session and then eventually go to the sensors part in the second part of the session, right? So there are two types of manufacturing process. One we call it as subtractive manufacturing, other we call it as additive manufacturing. This subtractive manufacturing is known to all mechanical engineer, which we call it as machining, where you have a raw material, you remove certain materials, you machine them, eventually you get the final product, right? In this particular case, it is spear. And what is happening, you have lot of waste material in this, right? Because of the machining, lot of chips and the wastage is coming, which leads to lot of wastage of the material. Needless to say, this wastage can be recycled, right, and can be again used for the starting of the material, but that will require additional energy and additional effort. But what happens in case of additive manufacturing process is this. What happens in case of additive manufacturing process, you have a starting material and you print it layer by layer, right? So if I slice this spear into maybe hundreds or 200s number of layer, what I'll do, I'll print each of the layer one upon another. So because of which the material wastage would be very less, right? And thus making of a product layer by layer by layer is what is called as additive manufacturing process, right? For example, this is one of the example where we want to manufacture this 3D object which has this hollow part. So how will I manufacture it? I'll have a cube, a solid cube. I'll use some of the drilling process in order to remove this material from this hole, right? And eventually I'll get the solid part. But here there are a lot of waste. But in additive manufacturing, what I'll do, I'll have a powder as a raw material and I'll heat this powder through a CNC system or through a robotic system, right? So what would happen? I'll make one layer, it will get melted, then another layer, so on and so forth, right? That is how this product would be made in a complete sense, and the wastage would be very less. Think of a situation where I want to have a spherical ball inside this 3D object. If I want to have a spherical ball inside the 3D object, then making that particular thing in machining will require a very complicated machining system, right? Maybe 5 axis or 6 axis. manufacturing process, it can be done very easily and quickly with a one third or maybe less than half of the cost. So those are the advantages of additive manufacturing process, right? So like I have already said, additive manufacturing is a technology that builds three-dimensional object by adding one layer upon another layer, right? We keep on doing that, right? And the biggest advantage of this additive manufacturing process, it can be done for any material. It can be plastic, it can be metal. Now people have even started talking about 3D printing of houses, right? That's why the concrete, biocompatible material, etc. Right? So why 3D printing process? Like I have already said, 3D printing process, it is at times it is very difficult to manufacture the complicated geometry, the sophisticated machine which is required. Every company or everybody cannot afford it. So that is why loss of material is very less in case of 3D printing process, and customized product. The biggest advantage of additive manufacturing process is customization. In industry, mostly people talk about mass production. In order to reduce the cost per piece, people want to produce the same product, maybe 100, 200, 1000 or 10,000 in number. But when it comes to additive manufacturing, I can manufacture each of the product with different feature and different geometry without increasing its cost, right? So by the customization, I'll not, with the help of 3D printing, I'll not require high tooling and mold cost, which is actually required in case of conventional manufacturing process, right? So what are the attributes of 3D printing? Like I have said, mass customization, right? Production of series of customized good. Each product can be different from other, right? Now, there are certain terminologies which everybody uses in 3D printing process. For example, additive, like even in this particular session, at times I have used 3D printing and at times I have used additive manufacturing. So what is the difference between 3D printing and additive manufacturing, if at all there is? And then there is another word which people use, which we call it as rapid prototyping. So let us first try to get clear what this different terminology means, right? So 3D printing and additive manufacturing are basically synonym words and can be used interchangeably, right? So whether I'm saying 3D printing or additive manufacturing, I'm talking about the same process. Then what is the difference? The difference is very simple. 3D printing is this particular word which is actually used by layman person, general public, media and all. They always talk about 3D printing because you are printing a three-dimensional object. But when you go to industry or when you talk about researcher, we generally don't use the word 3D printing. Instead, we use this word additive manufacturing because you're adding the material in order to manufacture it. That's why the word additive manufacturing, right? Then what is rapid prototyping? Rapid prototyping is one of the process under the category of additive manufacturing, right? So then what is the difference between additive manufacturing and rapid prototyping, which is RP? One, the cost of rapid prototyping process is very high, right? And the maintenance cost and initial cost is very high. 3D printing, the complexity 3D printing can take care of even with lesser training. So that's why nowadays people are, rapid prototyping process is eventually getting obsolete and people are going towards the this thing. So again, rapid prototyping, the basic mechanism of rapid prototyping is very similar to additive manufacturing process. It's just people have advanced that particular process in order to use it, right? So with this, let's come to the next part. How do we do this additive manufacturing? Meaning, what are the steps which are involved, right, in order to get the additive manufacturing process? So I have just shown you a flow diagram, right? So the first thing is 3D modeling. 3D modeling means you need to get a three-dimensional CAD modeling of the geometry which you want to make. How we can make it? So one way of making it, we can use any CAD software, CATIA, ProE, SolidWorks, or any CAD software, and with the help of that particular CAD software, this geometry can be made. That's one way. What is another way of making it? Reverse engineering. What is reverse engineering? Nowadays, there are a lot of cameras which are available, which you can scan, and that camera will give you the cloud data of points. And if you import this cloud data of point into any CAD software, it will give you the geometry. That is how people do the reverse engineering, right? So the CAD modeling can be done in either of the way, either through any CAD software or through scanning mechanism, which can be imported into CAD software, which can be used. Once we do that particular thing, then we need to create a STL file, which is stereolithography file, STL data, which this is an extension which is there in almost all CAD software, right? Once you are able to export this particular thing into the STL file, then what we need to do, we need to do the data preparation. And what is required in the data preparation? In data preparation, you need to prepare a file where you need to define various surfaces, like where is the open surface, where is the closed surface, where is hole, where is no hole. Then you need to also do the slicing. Slicing meaning, if you see this gear, right, let's say this gear has 20 mm of thickness. So now each layer would be of 1 mm thickness or 0.5 mm thickness. So if each layer is of 1 mm thickness, in order to make 20 mm, I require 20 layers, right? If I can even do the slicing less, I can make each layer thickness as 0.5, which basically means I need 40 layers. Now, reducing the slicing thickness or number of slices will increase the manufacturing time, right? So this is where, based on my understanding and the knowledge of additive manufacturing process, I need to create a balance. Once I do this particular process, then I need to generate the control data, meaning the XY movement, right? Because it's a three-dimensional thing. I need to generate the tool path planning, because most of the time additive manufacturing process is either done through CNC or through robotic arm. So I need to generate this control data, right? Tool path planning, where this heat source will move, and eventually you will produce a part. Once you produce the part, right, then comes the post processing. What we do in post processing, if there is any unwanted powder is over there, you remove it. You remove the support structure. Support structure meaning this additive manufacturing is done on the base plate, because wherever you will put the first layer, there would be a plate, and that plate is of no use. Eventually you need to remove that particular plate, right? So in post processing, we generally tend to remove this base plate. Then we at times used to do some kind of heat treatment process. If we think during additive manufacturing process there is some kind of a residual stress, or which requires some kind of annealing heat treatment process needs to be done, some kind of machining which needs to be done from the surface finish point of view, depending upon what process has been done, or some kind of polishing which is required. So any kind of post processing thing, be it machining, be it heat treatment, be it anything, right, would be done in the post processing category. And once it is done, right, then the entire process is completed, right? So if you have any query, please note it down, and eventually we can take it up one by one, right? And if you wish, you can stop me. I can answer the question there and there itself, and then we can move. So I am okay with both the modality, right? Now comes the application part. Now this application part is very interesting, because in application we will see in 3D printing process, it can be used for those kind of industrial application which requires a very high strength, right? For example, aerospace, automobile. On the contrary, for example, what you see in this particular current slide, right, it can be used for certain biomedical application, meaning if some has a accident, right, breakage of skull or something, right, through additive manufacturing process, that part can be manufactured and it can be sticked with the skull. For example, for dentist, for dental implantation, right, because each tooth has different geometry, different structure, this tooth can be actually manufactured using additive manufacturing process, right, so that the customization can happen, right? Certain other example is from the turbine industry or aerospace industry, where a lot of blades, turbine blades and all those things can be manufactured. These are turbine blades made up of inconel and titanium, right? Now the most interesting part is the construction one, which people are getting more fascinated, right? People are basically creating the entire house with the help of 3D printing process, right, where they basically extrude the concrete paste. They don't need to do the digging to get the pillars and all those things made, right? So this paste, the way we take out the paste from the toothpaste in the morning, similar way you have an extrusion system over here, from where you get the concrete which is coming out, and this entire system is moving in a particular direction, so that the house or the construction is happening in this particular way, right? This is one example. This is a free form home which has been manufactured by Wimberley, Allison, Tong and Company, right, through additive manufacturing process in a design competition. This is way back in 2016, right? So I think this has completed by now. Once this has happened, this is the world's first free from 3D printed house. So you see this kind of a structure is almost next to impossible with the what should I say, conventional construction process, brick by brick and all. Even though if it is possible, it will take a lot of time because of the sophistication, right? This I intentionally took this particular example. So there is an Indian startup called as Tivasta, right? This has been so the founder of this particular company are basically the alumni of IIT Madras, right? And they have founded this particular company, Tivasta. What they did as a demonstration purpose, they built this house. So if you see this beautiful house, right, this is made entirely out of 3D printing process, not through the conventional way, right? So just by seeing house, it is very difficult to find out whether it is through 3D printing and all, right? And this is a 600 square feet house, right? It was inaugurated by our finance minister, right? And it was only built within a week time, right? Only within a week's time this built. So can we imagine making a 600 square feet house within a week's time? On the contrary, if you want to make a 600 square feet house, it will at least take, from the structure point of view, it will at least take 6 months. So from specifically, there's another example, I have not shown it over here, but recently in IIT Guwahati, right, they built additive 3D printing toilets for army personnel, right? So there was a project which they completed and successfully they have given. So in a country like India, where there is a requirement to build millions of house in a quicker time, right? In order so that everybody has a house, what the government is planning, right? So for those kind of an application, making house in this particular way, in a mass scale, if we are able to get this kind of a machinery, it would be a huge achievement, right? So this is what is the potential of additive manufacturing process. Now with this, I would specifically like to discuss about this wire arc additive manufacturing process. Like I have already said, additive manufacturing process can be categorized into various categories. One is fuse deposition modeling, which is generally used for plastic. Then there is another is laser based. Laser based meaning the energy source in that particular thing is laser. That could be direct energy deposition or it could be powder bed fusion. Powder bed fusion meaning you have a table on which you spread the powder and the laser is passed through. So I think I'll show one figure. I think this one, right? This is one of the example of powder bed fusion where you have a table, there is one layer and you're passing it through the laser. So what would happen? Because of the laser passing, the sintering will happen. That's why the process is also called as selective laser sintering, where the particles are partially melted and the bonding happens, right? And the third category is arc-based additive manufacturing process, right? And the reason I want to emphasize on this arc-based additive manufacturing process over here is because this process is very handy, plus this process is very economical. For example, most of the institute, right, always have a welding machine, right? Now we are very well versed with MIG welding process, metal inert gas welding process, or TIG welding process, tungsten inert gas welding process. Now, if we smartly use this MIG welding and TIG welding process, we can get the wire arc additive manufacturing process. How? For example, let us see this schematic diagram. So what this schematic diagram shows, you have a base plate. Base plate meaning on which I want to make a particular geometry, right? Then I have a torch or the welding torch, and I have the electrode. In case of MIG, I have a consumable electrode. Now, what we normally do in case of welding, we have a consumable electrode. That consumable electrode melts and gets deposited onto the area which needs to be welded, right? What we create a melt pool, right? So we only put one layer of it, or if you are doing multi-pass, you put multiple layers of it, right? So this process is exactly similar with a difference. What we are doing with over here, instead of two pieces of plate, I have a substrate, and on that particular substrate I am depositing one layer upon another, right? So first I have one layer of the electrode. Once that one layer of electrode is done, then I'll have another layer, third layer, fourth layer, so on and so forth, right? With this particular thing, and if this system I attach with a robotic arm, let's say I have a 6-degree freedom robot, right, through which this my wire feeder is coming. So if I have a 6-degree freedom of robot, then what I can do, instead of making this layer like this, I can make it circular, right? Or I can make it elliptical, or I can make it some complicated shape which may not be possible for human being to do it manually. That is why when we talk about wire arc additive manufacturing process, automation of that particular process is very much important, either through a CNC system or through a robotic system, because maintaining the arc length with the help of hand is extremely difficult. It's practically not possible, right? Again, like in mechanical engineering, mostly you will find there are a lot of synonym names which are given. Similarly, if you go across the world, there are other names which are given to wire arc additive manufacturing process, which I'll now onwards I'll refer as WAM, WAAM, WAM process, right? What are the synonym names? Welding based deposition, because this is basically a welding technique and you're using for deposition. 3D welding or 3D micro welding. Why? Because end of the day you are doing the welding, but you're doing in a because you're getting a 3-dimensional object. That's why 3D welding. Hybrid layer manufacturing, safe deposition manufacturing, and wire arc additive manufacturing. So in India, the accepted nomenclature is WAM. Even in some of the European places where people do this, WAM is an acceptable term across community. Right? Now, let us try to understand what are the different types of wire arc additive manufacturing processes is available, right? Based on different things. So first of all, we see this is a category. So there are 3 categories of process. One is GTAW based, meaning gas tungsten arc welding process based. In other words, TIG based. So in TIG based, the energy source is again arc. In all the cases, the energy source is arc. But as we know, in TIG welding, you have a tungsten electrode, which is a non-consumable electrode. So one of the feature of this particular process, it has a non-consumable electrode. So either you need to have a powder, right, in place, the way we do in powder bed fusion, or we need to have a separate wire feeder which can be fed in, which can be used to generate this. What is the biggest advantage of this WAM process? See the deposition rate. The deposition rate for the WAM process is very high, 1 to 2 kg per hour. This is substantial, right? Which is very difficult to get with the laser based process, right? But again, both the process has its own advantages and disadvantages. And next, wire and torch rotations are needed in order to make a complicated shape. Now, the other possibilities, the way we know, we have MIG process, metal inert gas welding process, which you also call it as GMAW process. Through GMAW process, as we know, we have a consumable electrode. That's why one of the feature is consumable electrode. The deposition rate could be very high depending upon what is the feed rate of wire feeder. The only problem with this particular process, we get lot of spatter, right? In welding, we are very aware about if this wire is getting deposited in the molten pool, we get lot of spatter because of splashing. And the other problem is the arc stability. What is the solution? There is one more advancement which has happened, which people call it as cold metal transfer. What exactly is this cold metal transfer? All of you, when we study this welding process, we study different kinds of modes of metal transfer, meaning globular transfer, short circuit transfer, pulse transfer, and all those things. So this cold metal transfer is one of the type of short circuit transfer, right? How this short circuit transfer is achieved? What it does, there is a specific mechanism in case of this, right, where the consumable wire electrode reciprocate back and forth. Because this consumable wire electrode is reciprocating back and forth, right, along with the feed velocity, what you are trying to do, you are trying to introduce a short circuit metal transfer. And because you are trying to introduce this short circuit metal transfer, what is happening? The heat input which is coming is very low. So low heat input. If you have a low heat input, the distortion would be less. If distortion is less, your process tolerance would be very high, right? And because we are doing short circuit transfer instead of globular transfer, the spatter would be less, right? So again, this cold metal transfer is not a very new unique thing, but from the application point of view, people have created a condition by doing this reciprocating of consumable wire electrode, so that every time you get a short circuit metal transfer, right? This short circuit metal transfer is also possible in GMAW conventional, but there are specific conditions which will lead to short circuit transfer, and every time you don't get it, and that is how this technology got patented by one of the company. Then there is something called as tandem GMAW. What is tandem GMAW? Tandem GMAW meaning instead of one wire feeder, you'll have two wire feeder. So I have two consumable wire feeder. Now what advantage I have? Both this wire electrode can be same. For example, aluminium. That way my deposition rate increases. But at the same time, if I want to make intermetallic, what I can do? One wire feeder could be of aluminium, another wire feeder could be of steel. Because of this difference in wire feeder, what I'll get a composite, or I'll get an intermetallic, or I may even get the functionally graded material, right? So these are the advantages. The deposition rate is very high in this particular case, which is 6 to 8 kg per hour. So I mean, we can make big structures in a small period of time. What are the basic advantages? Easy mixing, because both the electrode move simultaneously, there is a control, so easy mixing. You can control the composition. What I can do, if required, I can have a higher feed rate for one material, lower feed rate for other material, depending upon what composition I want for the final product, right? And if you want to create functionally graded material or intermetallic material, this particular tandem GMAW can be very handy or could be very useful. The next in the list is PAW base. PAW base meaning plasma arc welding, right? Where we all know the heat source is arc, but it is through plasma, right? Plasma, we also know it's a fourth state of the matter, right? You basically ionize the gas in order to generate the plasma. That is how it is done. So energy source is through plasma. Again, in this particular case, we have a non-consumable electrode, and because we have a non-consumable electrode, either we need to have a separate wire feeder, right? Or we can even use powder. And once we use powder, we need to have a robotic system like I have shown it over here, right? It will generate the plasma arc source. The powder would be spread it over here, and you can move the plasma arc source as per the requirement, right? So like I have said, I'll again reiterate in this particular case, what happens in any of the wire arc additive manufacturing process, getting it done manually is extremely difficult, right? You can only do linear if you have a very good practice and all. So instead what people does, they make their own CNC system. Making a CNC system is not that complicated, or they at times purchase a robotic arm and integrate this welding setup with the robotic arm, right? So let us try to, so though I have not talked much about laser based additive manufacturing process, because my reason was I wanted to talk more about warm process. If I talk about laser based, then both the session will go in this additive manufacturing, and I would not have been able to focus on the IoT aspect of it, which I'll focus maybe from subsequent slides, right? So just to compare how this warm stands with direct energy deposition, the deposition rate is very low in case of laser based. It's hardly 0.1 kg or maybe 100 gram or 200 gram per hour. On the top hand side, it is 2 to 4 kg per hour, which is very high. The utilization rate of the power is very low, which is very high because you're using wire feeder over here, there is no problem at all. Suitable material, it can be used for titanium alloy steel. It can also be used for almost all kind of material. The manufacturing cost over is very high, right? Because it is very complicated. I mean, the capital cost of the equipment is high. In warm process, it is not that high because, like I have said, even your normal welding process with small modification can be used to make this warm. Applicable workpiece, both can generate complicated shape and small shape. Here also you can make large workpiece, but the only limitation is you can't make very large workpiece in case of DED. Manufacturing accuracy is very high in this particular case, which is almost close as 50 micron. The only problem over here is tolerance or the manufacturing accuracy, because it is entirely dependent upon your wire diameter, right? The lower the wire diameter, right, you will get better resolution, but in general it is as close as 200 micron, right? So what happens? So now let us see from the process map point of view, or let me just first talk about this particular defect, and then I'll talk about the process map, because from there I transition to this IoT, right? Why I want to talk about defect in this particular case? Because when I talk about IoT, so I will mostly focus on the real-time monitoring, how we can do the real-time monitoring using the sensor, and the entire data can be processed in an online mode, so that you can change the process parameter in the real-time way, right? So what is this? So as you see in the warm process, the major defect which happens in almost all type of additive manufacturing, one of them is porosity, right? Because the presence of gas or anything, then there is an oxidation, and then there is a crack. So these are the common defect which happen in warm, in arc welding, right, as well as in laser additive manufacturing. The other set of category of process is deformation. Deformation meaning because there is a large heat input involved over here, right, there could be thermal distortion, there could be residual stress, because of which you get a deformation. Lack of fusion. Lack of fusion meaning this, what is very similar to in the case of our welding, right? The penetration has not happened till the depth, right? Or a part of the area where the material should have present is not there. Surface defect, there are defects on the surfaces. Surface finish, the quality of the surface is not good, the surface roughness is very high. Geometric accuracy, we wanted to make a 10 mm diameter, let's say cylinder, instead of that you got 10.5 or 10.6, right? So what is the tolerance limit which is possible? Void. Another biggest problem in case of warm. One other problem is the interlayer porosity. Interlayer porosity mean, though it comes under the category of porosity also, but this interlayer porosity is another big problem. So when you're depositing multiple layers, what we need to do, we need to make sure the second layer which has been put onto the first layer is diffused properly with the first layer. If they are not mixing properly, then what would happen? Both will act as an independent layer, and if both of them act as an independent layer, we won't be able to get the required mechanical strength, right, which will create a lot of problem in terms of strength, right? We won't be getting the required strength because of this interlayer porosity. So this interlayer porosity needs to be managed very efficiently, and that can only be done by process optimization, right? So what are the process parameter over here? The current is one of the process parameter. Wire feed rate, that is one process parameter. Scan velocity or the travel velocity of the this feed wire is another process parameter. Tool path planning, right, that is one of the significant parameter. How we can control it? We can control through numerical simulation. So numerical simulation is one of the tool which is known to researcher for a very long time. We can do FE based or CFD based simulation, where we can, by changing the process parameter, we can see how output responses are varying, right? The third thing which has taken a lot of thrust in recent time, what we are talking about IoT, is basically real-time control of the process. Real-time control of the process meaning we can use various sensors, we can use different types of sensors, we can collect those data using those sensors. Once we collect those data using the sensor, then what we can do, we can process the data and we can identify certain feature. Based on those features, we can say whether the defect has come or not, right? Whether this product is defective or not. If this is defective, what kind of defect, right? All these things are possible using this usage of sensor. And once we are able to use this sensor, what we can do, we can process the parameter entirely on a real-time basis. And if you're doing the process parameter real-time basis, in the screen we'll get the output in real time, maybe at a delay of a second or a half a second. And once we know in real time whether there is a defect or not, what we can do, we can modify the process parameter in a way that from that point onwards there is no defect. That is why the real-time control of the process comes very handy, and this real-time control of the process is done through various sensors. This was done before also, but this was mostly done in offline mode, right? Now with the application of IoT and cloud computing and all, this entire thing can be done in a real-time mode, in an online mode, right? So this is what I would like to show it over here. So Dr. Ramakrishna. Hello.
Yeah, please continue. No, you may continue if you wish. If it's up to you totally.
No, I am fine. I can complete the entire session and then we can take the question answer.
Yeah, better. Maybe you can continue.
Yeah. Okay. Okay.
Yeah. Thank you.
Yeah. Thank you. Right. So what we are seeing over here in case of process map. So this is where this entire thought of IoT or real-time control mode start. So for example, this, just a second. Yeah. So what you see over here is basically the schematic, the photo of the experimental setup where you have a robotic arm, right? And this is the electrode where you are able to manufacture whatever you want, right? So what is the input? The input over here is power source, right? And then there's a positioner. Positioner meaning the tool, this tool path planning and all, right? And how do we are doing it? So like I have already said, we are doing the CAD modeling, then the slicing and generating the data and all. Then you're doing the path planning. Path planning meaning how this robotic arm will move, right? First it will go, let's say from 00 to 10-0, then to 20-0 to 25-0. How this will move? So you need to get the G code, M code, the way we talk in CNC. G code, M code we call it in CNC. Here we are talking in terms of tool path planning, where we need to tell the robotic arm how it will move. Once it is done, right, then we are doing the experiment, and when you're doing the experiment, we can capture various signal. How we can capture various signal? We can use closed circuit camera or high speed camera. It could be CMOS based or CCD based. We can use IR pyrometer. With the help of pyrometer, we can actually measure the temperature. We can use laser scanner. By the help of laser scanner, we can actually scan the surface area. Once we scan the surface area, right, we can see the surface property, and based on that, we can try to identify whether there is any kind of surface defect or not. With the help of all this data, we can do the real-time process monitoring, right? Once we have all the data, this data can be captured, and in order to process the data, we can create various kind of model, right? For example, it could be machine learning based model, it could be through wavelet analysis, it could be AI based, right? So depending upon the requirement, different kind of models can be made, and based on the output of this particular model, the tool path replanning can be done in a real-time basis, which will eventually do the process control, right? So this entire feedback will again go to this process monitoring, which will eventually change the data depending upon the requirement, right? For example, based on our past experience, we know if we increase the temperature, the melting rate will increase. And based on this, we found that the electrode is not melting properly, because of which you are getting a particular type of defect, right? So based on this modeling and the input, what can happen? The feedback can go to the system in real time. Please increase current by 10%, right? So if the current is increased by 10%, from 100 ampere it has gone to 110 ampere. So because of that, what happened? The melting rate will improve. Eventually that particular defect will get eliminated, right? That is what is the advantage, right? That is how it can be done. Secondly, the second advantage is because each of the sensors are connected through internet, right? Each one of us, even somebody sitting at home, can see the entire thing remotely. That is where IoT comes into picture, right? So what you are doing the same thing in the real time control and all those things, but your entire sensor and this thing is connected with the internet, which is you are seeing at a remote place through an app or through a screen, which is need not be at the location, but maybe at some different location, and from through that particular app you can alter the process, you can monitor the process, right? That is where, so real time processing, right? This plus use of internet, right, in order to get this information in the remote way and wherever we want to, is what is IoT all about, right? So if I go into internet and all those things part, I need to start talking about cloud computing and all those things, which I'm not focusing right now. So what we'll focus, we'll talk about various types of sensors, how these sensors can be used to capture data, how this data can be processed, right? Because eventually, even though whether you do offline or online, you need to process the data, and if you're able to process the data in online, we get the real-time advantage. If you do it in offline, the only advantage is you will improve the process in the next experiment, right? So let us first talk about different types of sensor, and the first sensor is basically the vision sensor. What is vision sensor? Vision sensor is nothing. There are a lot of laser scanner which are available in the market, which can scan the surface or the geometry, right? And for example, if you see this particular diagram, this is a chamber where this additive manufacturing is happening, and this is the laser sensor or the vision sensor is attached with this particular experimental setup. So what is happening? This particular thing is monitoring the entire geometry, the surface part of it, not internal part of it, but at least the surface part of it. For example, it can analyze the melt pool dynamics. Melt pool dynamics meaning, because you are melting the electrode, right? How this fluid movement is happening in the melt pool, right? This is very much important because the solidification of the material of this layer would be dependent on that, right? So understanding this melt pool dynamics is very important, right? We need to ensure that this melt pool, the liquid movement which is happening is not creating any kind of a problem in order to which is generating defects, right? Porosity or anything. Surface integrity. Now the surface integrity is very broad term. You can control what kind of surface roughness is giving, whether we are getting certain kind of geometry or not, whether we are getting surface, a particular type of finish or not. All these things can be monitored through surface integrity. Apart from that, what can you monitor? Melt pool width. What is the width? Melt pool height. What is the height of each layer? The morphology. All these things can be monitored through this laser scanner. So at least at the surface level, the vision sensor or this laser scanner can help us to generate all this data, right? For example, this is one of the output which is done by one of the researcher, right? What he has done various experiment, right? And this is showing 40 micron by 40 that particular area, right? And this is indicating different information. What is this indicating? First of all, this is an output of vision sensor. Once you get the output of vision sensor, you need to filter certain data in order to remove the noise. Once you have removed the noise, what you can see different pattern. For example, you see three nomenclature over here: U, O and N. What is U? U is indicating under melted, meaning the wire feeder which has come has not melted properly, because of which the product which you have got, right, has different kind of feature. It has not been fused properly, right? So this is because of under melting. What is N? N is normal melting, meaning the wire feeder has melted in a way which was desired, and O is indicating the over melting, right? For example, if you see this kind of a geometry, you can very easily see this is over melted, or in other words, from the technical point of view, the melt pool dynamics or the turbulence within the melt pool is so high, which has created this kind of a problem, right? This you can see under melting in this particular case, over melting in this particular case. So if with the help of vision sensor, if you are able to capture the melt pool dynamics, what can happen, all these images is already available in your database based on your digital twin and output. What would happen? Whatever images are coming, then there would be an image analysis, right? Image comparison analysis at the cloud or wherever you are doing, and it will see whether it is going under melted, over melted, or normal melted. If it is under melted, the output response would be please increase current by 10% or 15%, right? If it is over melted, the immediate output response of the feedback system would be reduce the current by 10% or 15%. And if it is normal, then go ahead with the process. So this way, right, during the process itself, the process can be improved, the process can be what should I say, enhanced in order to get a better product quality, right? So this is one example of using sensor where, and again, if you are connecting this particular sensor with internet, right? If somehow you're connecting this sensor with Wi-Fi and all, where you can store the data in cloud or any other location, then you can visualize this thing wherever you want, right? That is how this application of sensor eventually goes to IoT, right? But the real research is basically over here, right? Where you capture the data, you process the data, and how you interpret the data. That is what is in the monitoring sense is more important, right? Next in the list is spectral sensing. What is spectral sensing? There's a process which is called as optical emission spectroscopy, right? What is this process? This optical emission spectroscopy basically captures the wavelength of different material which is coming with the help of sensor, and this actually, depending upon the wavelength, tell you the composition. It is actually used for the composition analysis, meaning if I have an alloy, let's say an aluminum alloy, if I want to find out how much percentage of aluminum is there, how much percentage of copper is there, how much percentage of silicon is there, how much percentage of magnesium is there, I can find out that particular thing using OES analysis, which is an category of spectral analysis, right? So this output actually gives you elemental information, right? So in this signal, right, for example, if you see over here, this we are talking a schematic diagram where we are using this GTAW process in order to get the wire arc additive manufacturing process. Now what is happening, this arc data is, or the wavelength of this particular thing is captured using optical fiber through this spectrometer, and this data is eventually sent to a PC where you are processing it. How you are processing it? Let us see. You have got 4 different kind of wavelength. What has been shown over here is SOI 7K, 1K, 7D and 7K, right? And then you can use different filtering mechanism. Like for example, you can use FTT, right? Or you can use mean deviation, or you can do discrete wavelet analysis, any kind of processing technique, or you can use for Fourier transformation. So these are filtering techniques for the signals, and based on that, certain features can be captured. For example, if you see, there is a defect over here, right? And the feature over here is about a bit different. So this is indicator of seam oxidation, right? So the oxidation which is happening, so the feature of this thing is changing. Same is true for over here for crater, right? So you can do the mapping, right? This kind of mapping. For example, here you see there is a huge oxidation which has happened, which led to the change in the feature. Feature meaning the peak of this particular feature has changed the value, right? This kind of thing can be done, right? And it can also be used in order to get the phase. If there is any specific element which is coming more, that can also be helpful, and eventually we can understand the phase transformation which is happening. More important from the alloying. For example, we talked about this tandem thing. In case of tandem, if we are in case of a tandem wire arc additive manufacturing process, if I am using aluminium and steel both as the wire rod, right, and I want to see what kind of intermetallics is being formed, whether it is whether it has higher brittleness or lower brittleness, what kind of implication it will have in the overall product. All this thing is quite possible with this spectral sensing mechanism. Again, because this is eventually the data is stored in PC, right? PC can be connected to internet, right? Where the entire processing can happen either in location, or if this particular system is connected through internet, right, this can immediately transfer the data to cloud, and once the data is stored in the cloud, it can be downloaded or processed wherever we want using cloud computing, or the data can be downloaded remotely into some other PC and the processing can happen, right? So all these things are quite possible. Just we need to connect this sensor with the internet, right? For example, this is another example again for the just a second, yeah, correct. This is another example how the sensors can be used. For example, if you see an experimental diagram which has been done for wire arc additive manufacturing process, so you see a robotic arm over here which is connected with electrode and the power source and all, right? Then what you have a welding machine, and welding machine is connected with this pure argon and wire feeder, and this is eventually connected through this robot control cabinet, right? So that you can control, and this you are measuring the voltage and current. You're capturing the current and the voltage data. Why you're capturing the current and the voltage data? Because you want to see, by capturing the current and the voltage data, if I can get certain feature, if there is any, because if there is a defect, obviously there would be fluctuation in current, right? Because current is what is determining the melting and the heat generation and all those things. So if there is a defect or anything, right, there's a huge possibility that might be reflected in the current intensity value, or might be reflected in the fluctuation of the current. So you can't just capture the data, you need to process it also. For example, let us see this particular example, right? What these people have done, right, they wanted to map the intensity whatever has been captured, right, in order to get different types of defect. So what they have they have got the sparse polarity, small and dense polarity, porosity, sorry, not polarity, porosity, and no porosity case. So what you see over here, and this is through this output, the blue colored one which you see is through a sensor, and this one, this one is through X-ray, and this one is actual, right? Because they want to see whether the peaks which are coming is able to capture the location and all those things or not. So in order to do the validation, so what you see over here, right, you see the peaks or the intensity after doing FFT. So they have done this fast Fourier transformation, right? After doing the FFT and eliminating the noise and making signal to noise ratio proper, right, what they have done is they have found this kind of a graph where on y-axis it is intensity and x-axis it is basically the location. So what they are seeing, at certain cases there is a spike in peak, right? And when they tried to map this location with this product, they found at this location there was large porosity defects, right, which led to this particular understanding. If the peak or the intensity goes beyond a particular value, right, you can understand there is a defect, right? What kind of defect? Now if you see a large peak, it is indicating a large and the sparse porosity, and if you see the difference of the porosity, I mean the peak are basically less, right, these are small porosity. And here if you see, the intensity is more or less same, right? In all case the intensity is close to 1700 or 1800, that means you get no defect. So what you can do, or what a person or what an industrialist has done based on this information, if the peak value is very high, I need to understand it has a large porosity, the size of the porosity is very large, and accordingly I need to change the process parameter, right? If the peaks are deviating from the mean value by smaller thing, right, then what would happen? Then maybe there is a porosity, true, but the dimension of the porosity is very less, right? I mean these are small porosity, that means maybe if we tweak the process parameter maybe by 2 or 5%, it will be controlled, right? And if the peaks are consistent, then there is no requirement to modify the process parameter, right? And it can go very smoothly. Again, like I have said it previous, I'll say it again and again. I'll say it. This, if you're doing in offline mode, this is what is called as offline monitoring. If you're doing it in real time, right, you're capturing the data, processing in the real time, sending. If you're processing in the real time, that is what is called as real time monitoring. But if you have a feedback control also, meaning once you have processed this, based on that, if you're giving the feedback to the machine, back to the machine, for example, through this, if you see, it is back and forth, right? So if you are giving this back and forth information, again a feedback to the system, please increase this parameter by this much percentage, reduce this parameter by this much percentage, reduce wire feed rate by 5% or something like that, right? That way you can actually get a good output, right? Next in the list is acoustic sensor. I'm sorry, this image is, just a second. Just, sorry, right? So this is indicating, now acoustic sensor is one of the most efficient non-contact type sensor. So sorry for this overlap, so I'll just explain. So this is again a non-contact type sensors. So if it's a non-contact type sensor, you're talking about non-destructive testing technique, right? So even the both of the previous sensors was also of the non-contact type sensor. So you're talking about non-destructive technique, right? Which is very helpful, right? It, what this acoustic sensor helps you? Acoustic sensor helps you to understand, because it actually measures the arc sound, right? Acoustic sensors measure the sound. What you are interested in? You are interested to measure the arc sound. What kind of sound is generating through arc? And from this arc sound, you want to see study various things. What? You want to study defect. You want to study porosity, crack, which are type of defect. You want to study arc stability, right? Arc sound can give you lot of insight in terms of arc stability, right? So what you see over here, so the process is taking place, you have an acoustic sensor. So now the only problem with this acoustic sensor is you need an environment which has a pin drop silence, right? For example, if there is small voice or small noise which is happening in the experimental area, it will create a problem. It will not give you the good result. So what people used to do, when if they're using acoustic sensor, they used to perform the experiment at nights, 9 p.m., 10 p.m., where there is no person over there and the silence is pretty much, right? So the only drawback of acoustic sensor is if it captures the environmental sound or the nearby sound, then differentiating that sound with arc sound would be difficult. The only possibility is then you need to apply filters, right? Upper filter or lower filter, meaning if you know that the sound of arc will not be more than, let's say, 5 decibel or 10 decibel, and the environmental sound is higher than that, then you will basically filter out all the sound, the decibel value beyond a particular value. But the only problem is if the sound or the intensity of sound of arc is quite similar in terms of decibel, it is quite similar to what sound you are getting in environment, then filtering out would be extremely difficult, right? That is why in order to get efficient data, right, it is always better to perform this experiment where you have this soundproof room, or if not soundproof room, maybe at a place where the external sound will not create a problem. So what they do, they scan this particular thing. Again, what kind of filtering technique you will use, it's up to the user. Like I have said, it can be used as fast Fourier transformation, or at times if you just do the RMS value, root mean square of the signal data, it can give lot of features. You can do certain kind of wavelet analysis, not in case, but in case of vision sensor, you can do lot of image processing. All these are basically processing technique which is used after capturing the data, or I can say these are more like a data processing analysis. Sorry, data processing technique, not data processing analysis, data processing technique, right? So what they do, they measure the sound. The sound is measured through sensors, FBG sensor, as the name is there of one of the sound sensor. It is connected through optical fiber, right, and eventually connected to computer. Once you get this acoustic signal AE, right, then this acoustic signal you need to filter it out, right, you need to remove the noise and all, and then we need to get the features as per requirement. I can give you one example. For example, let us take one such application which was done by Pal et al, and this particular work was published in JMPT, Journal of Metal Processing and Technology, right? So what they did this arc welding or arc additive manufacturing, right? They used this pyrometer. Pyrometer was used to measure the temperature, and then they used this microphone. In order to capture the sound, the easiest was you to use the microphone, right? Very cheap, economical. They use the microphone in order to capture the arc sound, and obviously since it's a welding setup, it is connected to power source, and this microphone is eventually connected to data acquisition system, right? And once you have data acquisition system, you're basically capturing the data, right? Now once you capture the data, you do different kind of analysis. It could be time domain analysis or frequency domain analysis, it could be any of them, and based on this analysis you do the prediction of defect or metal transfer. Meaning, let's say they did this kurtosis analysis. This is one kind of analysis where you filter it. Now once they filtered the data, they found four different regions. So this is region 1, this is region 2, this is region 3, this is region 4, and this is region 4. And based on this kurtosis analysis, so this is the signal which was captured. They did this kurtosis analysis. This is the intensity, and what they found, if the data, kurtosis data is less than a particular value, here in this case is 5, right, there's a possibility that something has happened at that point of time. Why? Because if you see, there's a large change in this feature. The peak is largely different. In this particular case, the peak has a value of 15. In this particular case, the peak only has a value of 5. In this particular case, the peak only has a value of 2, right? In this case, the peak has a value of 10. So this is indicating, this kurtosis analysis indicating certain feature has changed, right? So the feature of the kurtosis analysis has changed. Now what we need to do, we need to we need to find out what thing has led to this change in the feature, right? And how we can find out? We can compare this particular thing, because x-axis is the region or the x-axis is the region or the length. So once they have tried to map it, what they have found, once they tried to map it, they found wherever this kind of thing has happened, there is a defect, right? For example, region 1, you see there is a defect. In region 2, if you see the bit size, it is fine, it is good, even though there is a smaller defect over here, right, closer to region 3, but it is fine. At region 3, because this value is very less, there is a bigger defect. There is a bigger defect. Here, everything is smooth, right? That is why it is indeed. So again, I'll repeat, the reason I'm not going in detail about this kurtosis analysis and all, there are many type of this processing analysis which is available, right? Time domain, frequency domain, like FFT, mean, RMS, square base, kurtosis, right? There are different types of filter, upper filter, lower filter, right? So lot of filters are available once you process it. So each filter may not be appropriate for a particular sensor. So you need to try out different filter, and that information we can also get from literature, right? Which particular filtering mechanism or the domain analysis is giving you distinct feature, is giving you certain feature which you can associate with defects, right? The way it has been done in this particular case, right? Next in the list is thermal sensing. What is thermal sensing? This entire temperature, right? This entire additive manufacturing process is temperature based. Temperature based meaning whether your temperature is high or low, it directly determines the difference in the thermal behavior. Difference in the thermal behavior meaning, if your temperature is very low, your feed wire will not melt. If it not melts, it will not create a proper first layer. If it is not creating a proper first layer, right, the bonding between the first and the second layer will not happen, right, leading to the interlayer porosity, right. If the temperature is too high, right, so there might be the viscosity of this liquid which will come, right, it would be very less, which will not be desired. This is one problem. What is the second problem? Temperature is that particular characteristics, right, which also governs the internal structure of the object. And when I say internal structure, I mean the microstructure, right, because temperature and deformation, right, are the two variables which govern the microstructure, right. And here the deformation is almost zero because we are not introducing any plastic deformation, so it is temperature. So somehow, if we are able to map the temperature data with the microstructure, we can even predict what kind of microstructural change will happen. That is what lot of people try to do in situ monitoring, right, in real time, based on the fluctuation of the temperature evolution, right. If there is any dip in temperature, or the temperature has become stagnant, or there is a sudden change in temperature, what kind of implication it will have in the microstructure, that is what lot of people have tried to establish. I was seeing the speaker list. One of the speaker will talk about this more in detail. I'll mostly focus on the defect. So what you see over here, so for example, this is IR first pass. IR is basically your IR camera, which if you see this particular setup, this is for TIG welding, or in other words, TIG based arc additive manufacturing process. Now here they have introduced an IR camera. Now this IR camera is trying to capture the temperature data from here through infrared, right? Infrared sensor. Now the only problem in case of infrared sensor is because it is entirely radiation based, right? You need to make sure the temperature which is capturing is only because of the temperature wavelength in of the workpiece. It should not be the reflection of the arc, right? Which is major problem in case of laser. So what happens in case of laser? Depending upon the reflectivity of the material, certain energy is absorbed and certain energy is reflected back. If energy, that reflected energy, if IR sensor is capturing, then it will not give you the correct value, right? So the only solution is you need to use certain amount of filter, because we know what is the wavelength of the arc which is generated. We can use the filter so that that particular wavelength is not captured using IR camera, and it is getting filtered out, right? That is one way of capturing it, right? And with this, what can be done? Please see again, this is another type of analysis by which you can do the defect analysis. Again, different types of defect, but primarily in this case defect. So what you see, if you have a IR first pass or second pass, meaning first layer or second layer, depending upon intensity, you can find some defect which is coming over here, which is not in this particular case, and same can be seen in the X-ray, the small amount, the porosity, what you see over here, right, which is not there in other length, in this part, right. So that way, this particular thermal sensing can also help you to get the information about defect, right. Now the next question which we need to understand is, we have talked about four different types of sensor: visual sensor, spectral sensor, acoustic sensor, and thermal sensor, right. And each of the sensor will have different what should I say, either somebody can use all of these four sensor, or in certain cases you might not use all the four sensor, you want to use only one or two of them. Then how do we identify which particular sensor gives what kind of thing, which one is cost effective, which one is most robust, and all those things, right. So this particular diagram evaluates all these four sensor in 6 different parameters. One is measurement range. So what is the range of the measurement, how far you can attach the sensor? The cost of the sensor, which is another important feature. The sensitivity of the sensor, how quickly the sensor can respond, right? So sensitivity talks about that particular information. Information complexity means how complex information or the data that particular sensor can capture. Robustness, how robust or how reliable that sensor is. And last but not the least, accuracy, right? So again, we are not talking about precision over here, accuracy. How close is the result of that particular sensor with the real one, right? So let us try to see it one by one. Let us first try to see the visual sensor. So if you see the visual sensor, the measurement range is maximum. So this is the center, which is 0, right? Extreme end is talking maximum, right? And this is 25%, 50, 75 and 100%, right? So for measurement sensor, the visual sensor, the measurement range is 100%. Comparatively, the cost is very less, right? Which is a good indicator, positive. But at the same time, the sensitivity is also less in comparison to spectral and acoustic sensor, right? So, but this is similar to thermal sensor. Why sensitivity is similar to thermal sensor? Because in thermal sensor, the wavelength of the arc and all those things also creates a problem. So, and the thermal sensor are not very sensitive. The resolution would be 1 degree centigrade or 2 degree centigrade. So this error range is generally high, right? Information complexity, it can capture all, like I have already told you, molten pool dynamics, pool width, height, all this information it can capture. That way, the robustness and accuracy is good, right? It's just the sensitivity of this particular sensor is bit less, meaning even though if there is a very small change, the sensor may or may not be able to capture it depending upon what kind of sensor you are using it, right? So this is about visual sensor. Next in the category is spectral sensor. What is the spectral sensor? We have already talked it about, and let us see the spectral sensor. Measurement range of the spectral sensor is very good. The cost of spectral sensor is no doubt very high, right? Because this captures the wavelength and all. So it is basically a sophisticated sensor, and it is very sensitive because each element exhibits different kind of wavelength, right? So if even though there is a small variation, it can give you an output, or the feature can vary based on that particular thing, right? Information complexity, you can't capture this molten pool dynamics and all those things. You can only get the elemental level information. That's why it cannot give you lot of information about uh, uh, various output responses, but it can give you only for the limited one, right? Robustness, there is a problem, right? This is not very robust for a very simple reason. If 2 or 3 element emits different kind of wavelength at a higher temperature, then distinguishing between those 2 or 3 element becomes difficult. Specifically, if the carbon content is there, then there is another challenge, because the way this spectral sensor work, it becomes difficult for the carbon, right? Accuracy, that's why moderately high accuracy. Now comes the acoustic sensor. Now acoustic sensor measurement range is good. Cost is the most minimum. Like you can use as simple as a microphone, right? If you don't want to go sophisticated. Sensitivity is high, but the only restriction is there should not be any sound from the surrounding. Otherwise, if you have a good microphone, it can capture even though there is a small change in the sound in terms of decibel. So sensitivity in that particular sense is very good, right? Information complexity, it is only capturing the sound, right? And this sound can only give you certain piece of information, will not give you the information from the mechanism point of view. Meaning, maybe like I have shown you in this particular case, with the help of this analysis, we can say there is a defect. But why this defect has happened, right? What change has happened in the molten pool dynamics because of which this defect has happened? This information, this acoustic signal may not be able to give you, but the visual sensor can give you, because you are able to capture the molten pool dynamics, right? So that kind of complexity visual sensor can handle, but acoustic sensor may not be able to handle. Is it robust? Yes, it is very much robust. It can be seen in this particular diagram. There is a clear, distinct difference in the feature, which is clearly indicating the defect. Same is true in this particular case. So there are a lot of evidence. I have only shown two case studies, two cases where people have used it, right? But there are a lot of studies which says the robustness and the accuracy of the acoustic signal is good. Last but not the least is the thermal sensor, right? So measurement range of the thermal sensor is not very high for a very simple reason. It can take, you can't keep camera at a very large distance because you need to focus it, right? It needs to focus at that particular region. If it is not focusing, it won't be able to capture the radiation which is coming, because thermal sensor, if you are not using K type thermocouple, if you are using IR base, it mostly works on the principle of radiation. Cost is comparatively high, right? Depending, I mean, it could be low cost also, but if you're going for a sophisticated, the cost can increase also. So you have a low cost thermal sensor as well as high cost thermal sensor. For example, pyrometer. Pyrometer is comparatively very cheap, right? But if somebody wants to have IR based thermal imager, then the cost would be high. So depending upon what kind of sensor we are talking about, the cost will vary. Sensitivity, the biggest problem with thermal sensor is most of the pyrometer and thermal sensor works for a particular range, meaning they will say it will work for a window of, let's say, minus 150 degrees centigrade to 200 degrees centigrade, or 400 degrees centigrade to 1200 degrees centigrade. So in between this range of 250 to 400, it will not get you the desired result. So because of this temperature window bands, right, at times it becomes difficult to capture the entire process phenomena, right? Information complexity, again it can capture because it can give you the reason, because molten pool dynamics will be a function of temperature, and temperature you are capturing using thermal sensor. Thermal sensor can also give you some information about defect. Thermal sensor can also give you some information about change in the metallurgical phenomena, mostly microstructure. So that way it is good. Robustness, it is slightly less for a very simple reason I have already told you. You need to filter out the wavelengths which is coming, which is not because of the temperature, instead it is because of the arc or because of the laser reflectivity. And that is why accuracy is slightly on the lower side. So in order to make this thermal sensor more accurate, right, what you need to do is multiple things. One, because most of the thermal sensor are IR based, emissivity, because we know it works on the principle of radiation, which is emissivity multiplied by Stephen Boltzmann constant multiplied by T to the power 4. Now this emissivity is a very variable thing. Why? Because this emissivity is a function of surface property, is a function of temperature. So lot of mistake what people does, they just Google it, and whatever emissivity is there for a particular material, they put it. For example, if emissivity of aluminium is 0.7, people will just blindly put 0.7 value. This is not correct. Why? Because if temperature is increasing, emissivity is a function of temperature. So emissivity will also change. So you need to change the emissivity depending upon the temperature range. If you're not changing the emissivity with a change in temperature, then accuracy would be lost. Second problem is emissivity is also a function of surface property, right? How much surface is roughness is there, how much waviness is there, and all those things. If surface is very smooth, emissivity would be different. If surface has waviness and all those things, emissivity would be different, right? So all these parameter, all these factors, right, creates a lot of error, right? And as a user who wants to do this analysis and all those things, have to be very careful so that these errors are eliminated and the sensors are used in an appropriate way, right? So what I would like to say as a conclusion over here is this. One, whenever somebody wants to use IoT for the real-time processing monitoring through this, they need to take care of two things. One, first they need to decide what kind of analysis they want to do, meaning whether they are interested to identify defect or not. If yes, what type of defect. whether they are interested to do microstructure analysis or not. If yes, then what kind of information you want. Based on this objective, then you need to decide what kind of sensor you want to use, right? Whether you want to only use acoustic sensor, whether you want to only use visual, whether you want to only use thermal, or combination of them and all. Then, depending upon what material you are choosing, you need to see whether the resolution of those sensors are appropriate or not, right? Thirdly, when you're using the sensor, you have to be very careful in terms of data capturing. Why? Because if you're not able to capture the data properly and there are a lot of noise which has been captured, you will not get the required information like this, what I was talking about in this particular case, or even in this particular case, the peaks. If there is too much noise in this particular information, filtering of the noise becomes very difficult, and that is one of the major challenge, right? And once it has been done, right, sufficient data needs to be captured. Lot of time, if you are taking one data per second, right, so the frequency of data capturing should be large enough so that you have sufficient data in order to process it, right? If you are doing one data per second and the entire process is of 10 seconds, you only have 10 data, and 10 data cannot give you the required information, right? So you need to get more information, at least 10 hertz or 20 hertz, right? 0.1 second per data, something like that. At least that level of sampling rate. Once you have that level of sampling rate, you'll have more data which you can process. What kind of processing you want to do, whether it has to be on computer or cloud computing, again depend upon requirement. But though people talk about cloud computing much, but even in the computer, this real-time processing can be done, and this computer can be eventually connected to the machine, right? That is also low-cost solution which lot of industries are interested nowadays, rather than operating remote. Remote operation, most of the industry, those have working environment which is not what should I say, appropriate for human comfort. For example, hot rolling mills, right, where the temperature is very high, right? It's not physically possible for human being to stay there for 5-6 hours. Maybe nuclear power plants, those kind of industry where human being cannot be present over there, the data can be taken into the cloud and it can be operated remotely, right? Thermal power plants, right? All this kind of industry are more interested in IoT, right, where they can add all this sensor, take the data, process it, and they can monitor it at a remote location, right? So with this, I would like to conclude it over here. Again, thank you very much for inviting me for this particular session. If there is any question, I would be more than happy to take it up.
Yeah, thank you, Rahul. Thank you, Dr. Rahul, for your nice explanation and well-made presentation. So, I think you, with your sound knowledge in this topic, you have enlightened each one of the participants. So, dear participant, if you have any doubts, please don't hesitate to ask him. He's a nice person to clear your doubts. He's a correct person. Any questions, even if it is small one, don't hesitate.
Please don't hesitate. I mean, you can put in the chat box, or you can unmute yourself and ask. Feel free. And if any one of you is interested to work in wire arc additive manufacturing process, feel free to write an email to me. We can see how we can do that.
And the participants' feedback link has been shared in the meeting chat. Maybe you can fill it meanwhile. Rahul, I just wanted to ask you one thing. Like I have worked on some metal forms, right? So is it also manufactured by the companies with the help of this additive manufacturing? And
Yeah.
I mean, can it be possible to make it with a 3D printer? Or what is the actual manufacturing process to make a like perfect perfect metal foam with like homogeneous porosity and all?
With additive manufacturing, theoretically it is possible, but the only challenge, because I have seen your work, so the foam which you make, those are the thickness of the layers are very less, right? And getting that small
Yes.
thickness is a challenge in case of additive manufacturing process. But yeah, through laser based, it's a possibility. But the most apt process would be powder metallurgy, right? Where
Okay. Yeah.
where you can, wherever you want to have porosity, you can add salt or some kind of those thing which can be eventually dissolved with some chemical. So you
Yeah, that's what I think. Vikrant Rajarlas, I think Vyas, they tried to
no,
make it with
that's a different process. That is through friction stir processing. So that's
yeah.
not a powder metallurgy. So what you do, you make the center. Yeah. So what you do this particular thing, but the centering part you do through friction stir processing. So I have not talked about friction stir welding case.
Yeah.
I worked in friction stir welding where there is a possibility of friction stir processing, where I stir this thing in the same location. So I generate the heat, and this heat will do the sintering part. The heat and the pressure will do the sintering.
Okay.
So that
But
is
actually,
possible.
yeah, I just wonder like how do they maintain like uniform like a porosity and then uniform like a pore structure within the as the porous itself is a complex geometry. Like how
Yeah.
do they able to manage by like in manufacturing the like complex geometry with so much precision?
100% uniformity is not possible, but with the help
Yeah.
of this friction stir processing, if your layer thickness is slightly thicker, with additive manufacturing it is 100% possible. It can manage.
So you mean to say like maybe additive manufacturing is best suited for some solid complex geometries or what?
Yes, it is actually. The only problem is what is the resolution.
Okay.
If your resolution is very low, then it creates a bit problem. Otherwise, yes, you can make, I can share some of the photos with you, right, where you can see lot of people have made this porous foam. But yeah, the only problem is if your length of this metallic part, right, which is a physical structure, is it is very thin, then the best possible is either powder metallurgy, where sintering could be any mechanism.
Yeah, okay. So another, I think I don't know whether it is relevant or not, but one fundamental doubt for me, like people are these days, like 3D printer is the most sophisticated technique to to manufacture some complex geometries. So is this like only plastic materials can be made with the help of 3D printer, or even metallic objects also can be made with 3D printer?
If you want to work on plastic, the machine would be different. If you want to work with metal, the machine would be different.
So
So,
both the ways it's available.
yeah, so plastic, metals, ceramics, even there are bio 3D printers. Bio 3D printers mean there are certain material which are considered as biocompatible material. For example, our skin,
Okay.
right? So if you're able to get those kind of a thing, those can also be 3D printed. But again, the sophistication in those cases is different. But plastic, ceramic, metals are well-known materials which can be very easily 3D printed.
Yeah, okay, okay. So, any more questions from the audience, please avail this opportunity, because he's a like craziest combination of doing experiments as well as the simulation. He's a nice person to clear your doubts. Yeah, don't hesitate to raise anything.
Fine, if there is no, you can send me through email also, so you can see, just drop it if in case you need it in future. So just message the email ID in chat box. If somebody wishes, can contact me in future also.
Okay, Dr. Rahul. It is a very nice and very impressive presentation. You covered most of the sensors, which covers variety of the applications. Thank you very much for your presentation, sir. Thank you.
Thank you. Thank you,
Thank
Doctor.
you. Thank you.
If there is no questions from the audience, maybe we can conclude the session. So, once again, thank you very much, Dr. Rahul, for readily accepting our invitation and being part in this wonderful FDP on applications of IoT in mechanical engineering. And we are very much glad to have you here today on this wonderful session on the need of IoT and applications of IoT in mechanical engineering. Thank you, Rahul.
Thank you, Dr. Ram. Thank you.
Thank you once again, all of you. Good night, and tomorrow we will meet at 6:45 p.m. Thank you, one and all.